Picture standing on Mercury where zinc melts beneath your feet at 800 degrees F. Now imagine Mars where your breath freezes solid at minus 200 degrees F. Between these extremes sits one planet at exactly the right distance from our star. Not too hot, not too cold, but just right for liquid water. Scientists call this narrow band the Goldilocks zone. Move Earth just 5% closer to the sun, and our oceans boil away. Move us 5% farther, and they freeze solid. We exist in a band representing less than 3% of our solar system's total width, like walking a tightrope across the Grand Canyon. Earth has maintained this perfect distance for over 4 billion years. When our solar system formed from spinning gas and dust, countless random factors determined where each planet would end up. Venus missed the habitable target by 25 million miles, becoming a hellscape of sulfuric acid rain. Mars missed by a similar distance in the other direction, becoming a frozen desert. Yet Earth landed exactly where complex chemistry could flourish. The odds, a number with more zeros than atoms in the observable universe. The Moon's perfect design. Hanging 239,000 miles away, our Moon appears almost identical in size to our Sun during eclipses. An extraordinary coincidence, but this is just the beginning. Every 6 hours, the Moon pulls our oceans into tides that mix nutrients through seawater, keeping it rich with chemicals life needs. Without tidal mixing, our seas would become stagnant, lifeless layers. The Moon also acts like a cosmic metronome, keeping Earth spinning steadily. Mars, with 2 tiny moons, wobbles wildly on its axis. Sometimes its poles point directly at the Sun, creating temperature swings of hundreds of degrees that would sterilize life. Earth's large moon locks our tilt at 23.5 degrees, creating gentle seasons. Remove the Moon tomorrow and Earth would tumble chaotically through space like a broken gyroscope. Scientists calculate a moon must be exactly the right size relative to its planet. Too small, no influence. Too large, tidal forces crack the planet's surface. Our Moon represents exactly 1/4 of Earth's size, a ratio found nowhere else in our solar system. How it formed makes this more incredible. 4.5 billion years ago, a Mars-sized object called Theia smashed into early Earth at exactly the right angle and speed. Hit too directly, both destroyed. Too shallow, Theia bounces off into space. Instead, the collision blasted exactly the right amount of material into orbit to form our perfect Moon. The odds, like throwing a dart from space and hitting a bullseye on Earth. Jupiter, the cosmic guardian, 2.5 times farther from the Sun, orbits a giant so massive it could swallow Earth like a marble into a basketball. Jupiter weighs more than twice all other planets combined, creating a gravitational field that acts as our solar system's cosmic vacuum cleaner. In 1994, astronomers watched comet Shoemaker-Levy 9 crash into Jupiter's atmosphere. The impact created explosions larger than Earth, releasing more energy than every nuclear weapon ever built. That comet was heading toward the inner solar system, possibly toward us. Jupiter caught it first. Computer simulations show that without Jupiter's gravitational influence, Earth's orbit would gradually decay, sending us spiraling into the Sun. Jupiter sits at exactly the right distance to provide maximum protection without disrupting our orbit. Most star systems don't have a giant planet positioned like Jupiter. Instead, they contain hot Jupiters orbiting close to their stars, creating gravitational chaos that flings Earth-like planets into deep space. The magnetic shield. Streaming toward Earth at over 1 million miles per hour comes solar wind, carrying charged particles that could strip away our atmosphere in minutes. The only reason you can step outside is our planet's invisible magnetic field. Deep beneath your feet, 1,500 miles below the surface, liquid iron churns in Earth's outer core at temperatures hotter than the Sun's surface. This creates electrical currents generating a magnetic field extending 60,000 miles into space, the magnetosphere. When solar particles hit this field, they create the aurora borealis, painting polar skies with green and blue light. Mars once had a magnetic field, but its smaller size meant its core cooled and solidified billions of years ago. Without protection, solar wind stripped away most of the Martian atmosphere. Venus also lacks a protective field. Only Earth maintains the perfect balance of planetary size, core composition, and rotation speed needed to sustain a magnetic field for billions of years. The strength is precisely calibrated. Too weak, radiation erodes our atmosphere like Mars. Too strong, the field traps so much solar energy it cooks the surface. This invisible shield has remained stable for 4 billion years, protecting the delicate chemistry that creates life. The perfect air. Take a deep breath. You're inhaling a mixture so precisely balanced that changing any component by just a few percentage points would make Earth uninhabitable. Our atmosphere contains exactly 21% oxygen, 78% nitrogen, and traces of other gases, the only known air mixture in the universe that can support complex life. Increase oxygen to 25%. Every spark triggers massive fires that could burn continents. Reduce to 16%. You slowly suffocate while breathing normally. Nitrogen creates atmospheric pressure that keeps liquid water stable. Without enough, water boils away. Too much pressure prevents evaporation, stopping the water cycle. Carbon dioxide at 400 parts per million creates just enough greenhouse warming to keep Earth above freezing. Double it, runaway heating turns us into Venus. Cut it in half, ice covers the planet permanently. This balance took billions of years to achieve. Early Earth had methane and ammonia, instantly lethal to modern life. Gradually, photosynthetic bacteria produced oxygen over 2 billion years. During the Great Oxidation Event, oxygen levels rose so dramatically they poisoned most existing life, clearing the way for oxygen-breathing organisms. Remarkably, oxygen stabilized at exactly 21% and has remained there for hundreds of millions of years. Water, the impossible molecule. Water should be a gas at Earth's temperatures. When chemists compare its molecular weight to similar compounds, all equations predict water should boil at -100 degrees F. Instead, water remains liquid across the exact temperature range where life survives. This happens because water molecules stick together through hydrogen bonds, giving water properties found nowhere else. Water expands when it freezes, making ice float. If ice sank like every other solid, Earth's water would freeze from the bottom up into a planet-wide ice cube that never melts. Floating ice insulates liquid water underneath, allowing life to survive even during ice ages. Water holds more heat than almost any other substance, making it perfect for temperature regulation. Oceans store vast amounts of heat and release it slowly, preventing extreme temperature swings. Water dissolves more substances than any other liquid, the universal solvent, carrying nutrients, minerals, and waste throughout organisms. Water molecules form the perfect scaffolding for biological molecules. DNA, proteins, and other essential components fold into functional shapes because of how they interact with surrounding water. Change water's properties slightly, and these molecules unfold and stop working. The amount is precisely calibrated. Twice as much, no land exists above sea level. Half as much, most continents become uninhabitable deserts. Earth's perfect spin. Earth completes one rotation every 24 hours, calibrated so precisely that changing it by a few hours would make our planet uninhabitable. If Earth spun twice as fast, 12-hour days, the faster rotation would create 300 mph winds that level every building and uproot every tree. Now picture Earth spinning half as slow, 48-hour days. The sun would bake one side to over 200 degrees F, while the night side froze to -150 degrees F. Our 24-hour rotation creates perfect balance, allowing the sun to warm Earth without overheating, then giving time to cool without freezing. This rhythm has remained stable for billions of years, even though the moon gradually slows Earth's rotation by about 1 second every 50,000 years. The rotation speed creates the Coriolis effect, driving weather patterns and ocean currents that distribute heat around the globe. It also generates Earth's magnetic field by stirring molten iron in our core. A slower rotation weakens this protection. A faster rotation might create such a strong field it overheats the planet. The perfect tilt. Earth tilts on its axis at exactly 23.5 degrees, creating gentle seasons that have allowed life to flourish for billions of years. Without any tilt, the equator would remain blazingly hot year-round while poles stayed frozen, limiting life to a narrow band. Increase the tilt to 45 degrees and seasons become so extreme they sterilize most of the planet. During summer, tilted hemispheres would receive direct sunlight for months, boiling water. During winter, regions would plunge into darkness so cold even oceans begin freezing. Mars tilts at 25 degrees, very close to Earth, but lacks a large moon to keep this stable. Over thousands of years, Mars wobbles between 15 degrees and 35 degrees, creating dramatic climate changes preventing stable conditions. Earth's 23.5 degrees tilt creates perfect balance. Summer melts winter snow, providing fresh water. Winter freezes harmful bacteria and pests. Spring and fall provide transition periods allowing gradual adjustment. This tilt drives seasonal migration patterns, shaping evolution for millions of years, and created agricultural cycles that allowed human civilization to develop. Our safe galactic neighborhood. Earth orbits the Sun in the quiet suburbs of the Milky Way, 26,000 light-years from the galactic center, exactly where life can survive cosmic dangers. Move half that distance closer, and deadly radiation from the supermassive black hole at the galaxy's heart would strip away our atmosphere. Near the galactic center, stars pack so densely that gravitational interactions constantly disrupt planetary orbits. Massive stars explode as supernovas, creating radiation waves that sterilize nearby planets. The galactic center also harbors a black hole containing 4 million solar masses, occasionally releasing bursts of X-rays and gamma rays powerful enough to destroy ozone layers hundreds of light-years away. Our solar system travels through the galaxy at exactly the right speed to avoid most hazards. We orbit once every 230 million years, moving fast enough to stay ahead of spiral arms where most supernovas occur. Our local neighborhood, the local bubble, was carved out by ancient supernovas that cleared away interstellar gas and dust that could interfere with planetary development. The Sun's position places us in a zone with just the right abundance of heavy elements. Closer to the center, frequent supernovas enrich space with metals, but radiation is too harsh. Farther out, insufficient heavy elements for rocky planets. The fine-tuned universe. The universe operates according to fundamental constants that appear fine-tuned to an impossible degree. Gravity holds you to Earth with precisely the right strength. Increase gravity by just 1 part in 1036, and stars burn out in millions of years instead of billions. Decrease it by the same amount, and gravity is too weak to form stars at all. The strong nuclear force binds protons and neutrons with exactly the right strength to create the periodic table. Make it slightly weaker. Atomic nuclei fall apart, leaving only hydrogen. Slightly stronger, all hydrogen fuses into heavier elements, leaving no fuel for stars and no water for life. The electromagnetic force governs how electrons orbit nuclei and atoms bond together. Change its strength by more than 4% in either direction, and carbon cannot form complex molecules. Chemistry, as we know it, would be impossible. The weak nuclear force controls radioactive decay and reactions powering stars. Without this calibrated exactly right, stars couldn't convert hydrogen into heavier elements. The expansion rate of the universe appears perfectly tuned. Too fast and matter spreads too thin for structure formation. Too slow and the universe collapses before stars form. Cosmologists have calculated that fundamental constants must fall within incredibly narrow ranges for a universe supporting life. The odds of this happening by random chance are so small you would need more universes than atoms in our observable cosmos to expect it to occur even once. The precision of nuclear forces. Inside every star, nuclear forces work with clockwork precision to forge elements making your body possible. The strong nuclear force holds protons and neutrons together despite electromagnetic force pushing protons apart. This balance is calibrated so precisely that changing the strong force by just 2% would make carbon atoms impossible to create. Inside massive stars, hydrogen fuses at 100 million degrees, building heavier elements step by step. First hydrogen to helium, then helium to beryllium, which immediately decays unless it captures another helium nucleus in a tiny fraction of a second. This creates carbon through a process so unlikely astronomers initially thought it impossible. The nuclear resonance allowing carbon formation was predicted by astronomer Fred Hoyle before it was discovered in laboratories. Hoyle calculated carbon production required a very specific energy level, and physicists found it exactly where he said it would be. Nuclear forces also create oxygen through another precisely calibrated resonance. Make the strong force slightly stronger. Carbon burns too easily into oxygen, leaving none for life. Slightly weaker, oxygen cannot form at all. When massive stars exhaust nuclear fuel, they explode as supernovas, scattering heavy elements throughout space. These explosions are powerful enough to forge elements heavier than iron. Nuclear forces are calibrated, so supernovas produce exactly the right mixture of elements for rocky planets and biological chemistry. Carbon, the versatile element. Carbon atoms possess unique ability to bond with themselves and other elements in ways making life's complex chemistry possible. Each carbon atom can form 4 strong chemical bonds, allowing it to connect with other carbons in chains, rings, and 3-dimensional networks of almost unlimited complexity. Silicon, carbon's closest chemical relative, can only form long chains in artificial laboratory conditions, and these break apart when exposed to water or oxygen. Carbon's bonding ability allows it to create millions of different molecules from just a few atom types. Combine carbon with hydrogen, oxygen, nitrogen, phosphorus, and sulfur. You can build DNA, proteins, fats, carbohydrates, and every other molecule making life work. Carbon chemistry works perfectly in water, forming stable bonds that resist breaking randomly while remaining flexible enough to change when needed. This balance allows biological molecules to maintain shapes long enough to function, while still being able to react and evolve. Carbon forms DNA's backbone, the molecule storing genetic information in every living thing. The double helix depends on carbon atoms forming a sugar phosphate backbone, giving the molecule stability, while allowing genetic code to be read and copied. Proteins fold into complex shapes determined by their carbon-based amino acid building blocks. These shapes allow proteins to catalyze reactions, transport materials, provide structural support, and carry out thousands of tasks keeping life functioning. The origin of life. 4 billion years ago, in a warm tide pool on early Earth, molecules began doing something that had never happened in the universe's history. They started making copies of themselves. The leap from simple chemistry to self-replicating life represents one of the most improbable events ever. Scientists calculate the odds of random reactions, producing a molecule capable of copying itself, are less than 1 in 1040,000. There are only 1080 atoms in the entire observable universe. The first self-replicating molecule had to solve an impossible puzzle, complex enough to carry information about building itself, yet simple enough to form spontaneously from early Earth's chemical soup. This molecule had to be stable enough to survive harsh conditions, while remaining flexible enough to make copies and occasionally change through mutations. DNA is far too complex to have formed spontaneously. Its double helix contains billions of precisely arranged chemical letters. Scientists believe life began with RNA, a simpler cousin that can both store information and catalyze reactions. However, even the simplest self-replicating RNA contains dozens of precisely arranged components. The RNA world hypothesis suggests early Earth contained countless different RNA molecules, most doing nothing useful. Through incredibly unlikely chance events, one RNA molecule developed ability to make imperfect copies. These copying errors occasionally produced molecules better at surviving than their parents. This molecular evolution required delicate balance. Too many copying errors, genetic information becomes scrambled. Too few, life never evolves beyond the first simple molecule. The mutation rate had to be precisely calibrated to allow improvement while maintaining stable inheritance. Mass extinctions, evolution's reset button. Throughout Earth's history, massive extinction events have struck with the precision of a cosmic sculptor, each catastrophe removing exactly the right species to allow more complex life to flourish. The most famous occurred 66 million years ago, when a 6-mile-wide asteroid slammed into Earth with the force of 10 billion atomic bombs. This wiped out dinosaurs, but cleared ecological niches, allowing small mammals to diversify and eventually evolve into every mammalian species today, including humans. Without this perfectly timed catastrophe, dinosaurs would likely still dominate. These successful reptiles had ruled for over 160 million years. Mammals remained small nocturnal creatures living in reptilian shadows. The asteroid reset evolution's clock, giving mammals opportunity to grow large and develop complex brains, eventually leading to human intelligence. The timing was crucial. Too early, mammals wouldn't have evolved enough to take advantage. Too late, dinosaurs might have evolved intelligence first. The Great Dying 250 million years ago was even more devastating, eliminating 96% of marine species and 70% of land vertebrates, nearly ending life entirely. Yet this cleared the way for dinosaurs to evolve, setting the stage for later mammalian takeover. Each major extinction removed dominant life forms, preventing other groups from diversifying. The pattern suggests extinctions serve as reset buttons for evolution, preventing any single group from permanently dominating Earth's ecosystems. The photosynthesis revolution. 3 billion years ago, tiny bacteria floating in ancient oceans began performing a chemical trick, transforming Earth from lifeless rock into vibrant biosphere. Early cyanobacteria discovered how to capture energy directly from sunlight and use it to build organic molecules from carbon dioxide and water. Before photosynthesis, life survived on starvation diet, extracting small amounts of energy from chemicals dissolved in seawater or produced by volcanic activity. This energy scarcity kept life simple and rare. Photosynthesis unlocked an energy source 10,000 times more abundant. Sunlight bathes Earth's surface with enough energy every hour to power human civilization for an entire year. Cyanobacteria learned to tap this vast reservoir, creating the foundation for all complex life. The most remarkable part is photosynthesis's ability to split water molecules, one of the most chemically stable compounds in the universe. Breaking apart water requires enormous energy, yet cyanobacteria do this using nothing but sunlight. This water-splitting reaction produces oxygen as waste, beginning Earth's atmospheric transformation. For over 1 billion years, photosynthetic bacteria pumped oxygen into the atmosphere while removing carbon dioxide. This great oxidation event poisoned most existing life evolved in oxygen-free environments. Yet this atmospheric transformation made complex life possible. Oxygen-breathing organisms extract 20 times more energy from food than organisms without oxygen. This abundance allowed life to grow larger, move faster, and develop sophisticated structures like eyes, brains, and nervous systems. Photosynthesis also created the ozone layer, protecting Earth's surface from deadly ultraviolet radiation, allowing life to leave oceanic depths and colonize land. Plate tectonics, Earth's recycling system. Beneath your feet, massive rock slabs called tectonic plates drift across Earth's surface at the speed fingernails grow, constantly recycling our planet's crust and maintaining perfect conditions for life. Plate tectonics operates like a planetary conveyor belt, running without interruption for over 3 billion years. New seafloor forms at underwater volcanic ridges, where molten rock rises from Earth's interior. This crust spreads outward, carrying continents like passengers on a slow-moving raft. When oceanic plates collide with continental plates, denser oceanic crust plunges back into Earth's interior. This geological recycling regulates Earth's climate by controlling atmospheric carbon dioxide. When CO2 levels rise, more rock weathering occurs as gas dissolves in rainwater, forming weak acids. This weathering pulls CO2 from the atmosphere and locks it in limestone. When CO2 drops, reduced weathering allows volcanic emissions to gradually restore atmospheric levels. Without plate tectonics, Earth would have become uninhabitable billions of ago. carbon dioxide would have accumulated until runaway greenhouse heating turned Earth into Venus with surface temperatures melting lead. Alternatively, all CO2 might have locked away in rocks, creating a frozen planet. Venus and Mars both lack active plate tectonics, and both became uninhabitable. Venus has too much CO2, creating 900 degrees F surface temperatures. Mars lost most of its CO2 to space because it had no geological recycling system. Plate tectonics also concentrates vital nutrients where life can access them. Colliding plates build mountains, exposing fresh rock to weathering, releasing phosphorus, nitrogen, and other elements life requires. The recycling of ocean crust helps maintain seawater's chemical balance. The greenhouse gas balance. For 4.5 billion years, Earth's atmosphere has maintained exactly the right greenhouse gas mixture to keep our planet warm enough for liquid water, but cool enough to prevent runaway heating. During the early solar system, the sun burned 25% dimmer than today. This weaker output should have frozen Earth's oceans solid, creating a planet-wide ice sheet reflecting so much sunlight Earth could never warm again. Instead, Earth's early atmosphere contained much more carbon dioxide, creating stronger greenhouse warming compensating for the dimmer sun. As the sun gradually brightened over billions of years, atmospheric CO2 dropped by almost exactly the right amount to maintain stable temperatures. This perfect balance required incredibly precise timing. If CO2 decreased too quickly, Earth freezes. Too slowly, we overheat like Venus. The mechanism accomplishing this fine-tuning involves rock weathering, which accelerates when temperatures rise and slows when temperatures fall. Warmer temperatures increase rainfall and speed reactions, dissolving CO2 into rainwater. This CO2-rich water reacts with rocks, removing CO2 from the atmosphere and storing it in limestone. When Earth's temperature rises, increased weathering pulls more CO2 out, cooling the planet. When temperatures drop, reduced weathering allows volcanic emissions to increase atmospheric CO2, warming things back up. This natural thermostat has operated automatically for billions of years. The narrow window for intelligent life. Complex life on Earth evolved during a narrow window of opportunity, rapidly closing as our sun grows hotter and brighter with each passing million years. Stars like our sun follow predictable aging, increasing their energy output over billions of years. The sun today burns 10% brighter than when life first appeared and will continue brightening until it expands into a red giant in about 5 billion years. But complex life didn't have 5 billion years to evolve. Steady increases in solar brightness mean Earth will become too hot for life much sooner. In approximately 1 billion years, increased solar heating will trigger runaway greenhouse effects, vaporizing our oceans and stripping away our atmosphere, turning Earth into Venus. This creates a cosmic deadline for evolution. Life had roughly 3.5 billion years from its origin to develop intelligence and technology before Earth becomes uninhabitable. Remarkably, complex life appeared and evolved intelligence almost exactly when it needed to beat this deadline. For the first 2 billion years, life remained microscopic. Complex cells with nuclei didn't appear until about 2 billion years ago. Multicellular organisms with specialized tissues didn't evolve until 600 million years ago, using up most time available for complex evolution. Intelligence evolved even more recently, appearing in human ancestors only within the past few million years. Modern humans developed agriculture and technology within the past 10,000 years, incredibly short compared to billions of years life has existed. The emergence of intelligence appears to be a rare, difficult evolutionary achievement. Despite billions of years and countless species, only one lineage on Earth has developed intelligence capable of understanding the universe and building technology to explore space. The rarity of intelligence. In 4 billion years of evolution on Earth, intelligence advanced enough to understand the universe has emerged exactly once, suggesting consciousness might be the rarest phenomenon in the cosmos. Life appeared on Earth almost as soon as conditions allowed, roughly 3.5 billion years ago. Since then, evolution has produced millions of species with countless survival strategies, body plans, and ecological adaptations. Yet only one species has developed cognitive abilities to build telescopes, decode DNA, and contemplate its place in the universe. This suggests that while life might be common throughout the cosmos, intelligence could be extraordinarily rare. Many evolutionary pathways lead to successful survival strategies not requiring large brains or complex reasoning. Bacteria have thrived for billions of years without intelligence. Insects dominate through instinct rather than conscious thought. Even among animals with nervous systems, intelligence remains limited to a few lineages. Dolphins, elephants, and some primates show signs of self-awareness and problem-solving, but none have developed language complex enough to accumulate knowledge across generations or technology sophisticated enough to modify their environment significantly. The evolution of human intelligence required incredibly specific environmental pressures and genetic changes. Our ancestors lived in African forests, gradually giving way to savannas, forcing adaptation to open grasslands. This transition favored bipedalism, tool use, and social cooperation, all contributing to brain development. Climate instability during ice ages created additional pressure for cognitive advancement. Early humans faced rapidly changing environments rewarding flexibility, planning, and cultural learning over fixed instinctual responses. Language represented another unlikely breakthrough, separating humans from other intelligent species. Language allows knowledge to accumulate across generations, creating cultural evolution operating much faster than biological evolution. The Drake equation. Astronomer Frank Drake created an equation in 1961, attempting to calculate how many communicating civilizations exist in our galaxy, revealing how many unlikely factors must align for intelligence to emerge. The Drake equation multiplies 7 variables: star formation rate, fraction of stars with planets, number of habitable planets per system, fraction developing life, fraction evolving intelligence, fraction developing technology, and how long technological civilizations survive. When Drake first proposed his equation, astronomers knew almost nothing about planets around other stars. Today, space telescopes have discovered over 5,000 exoplanets, revealing planetary systems are common. Nearly every star appears to host at least one planet. However, finding potentially habitable planets has proven much more challenging. Most discovered exoplanets are gas giants or rocky worlds orbiting too close to their stars to maintain liquid water. The few Earth-sized planets found in habitable zones often orbit red dwarf stars that bombard them with deadly radiation. Even more restrictive are requirements for complex life discovered through studying Earth's history. A planet needs not just right temperature and atmospheric composition, but also plate tectonics, a large moon for stability, protective magnetic field, a gas giant to shield it from asteroids, and location in a stable galactic region. When astronomers factor in all these requirements, the number of truly Earth-like planets drops dramatically. Some estimates suggest planets with all conditions necessary for complex life might be separated by hundreds or thousands of light years, even in a galaxy containing over 100 billion stars. The emergence of life itself remains a complete mystery. Despite decades of research, scientists have never successfully created self-replicating molecules from non-living chemicals, suggesting life's origin might be extremely rare. Recent calculations using updated Drake equation values suggest Earth might be the only planet in our galaxy currently hosting intelligent life. Beyond Earth, whether Earth was designed by cosmic accident, divine intention, or advanced programmers, humanity now faces the profound responsibility of carrying consciousness and life beyond our home planet before it becomes uninhabitable. The perfect conditions that created and sustained life on Earth are temporary. In approximately 1 billion years, increasing solar brightness will trigger runaway greenhouse heating boiling away our oceans. Long before that deadline, climate changes, asteroid impacts, or other catastrophes could end human civilization. This cosmic time limit transforms space exploration from interesting option into survival imperative. Humanity must develop technology to establish self-sustaining colonies on other worlds within the relatively brief window remaining before Earth becomes uninhabitable. The search for habitable exoplanets has revealed Earth-like worlds are extraordinarily rare. Most planets are gas giants, frozen ice balls, or scorched rocks. The few potentially habitable worlds discovered are dozens or hundreds of light years away, requiring revolutionary propulsion advances. However, humans might not need perfect Earth clones. Advances in genetic engineering, artificial intelligence, and life support could allow our species to adapt to planetary environments lethal to unmodified humans. Mars represents humanity's most accessible stepping stone to becoming multiplanetary. Despite thin atmosphere and freezing temperatures, Mars has water ice, carbon dioxide, and mineral resources that could support colonies using advanced technology. The 26 great coincidences that led to your existence have created a species capable of understanding its place in the cosmos and taking action to preserve consciousness beyond its planet of origin. Whether this represents fulfillment of cosmic design or the ultimate achievement of natural processes, humanity now carries the extraordinary privilege and responsibility of becoming gardeners of consciousness among the stars. Your existence in this perfectly tuned universe is not just a cosmic accident to be grateful for, but a call to action to ensure that the spark of awareness that began on Earth continues to shine throughout the galaxy for billions of years to come.